Okay, we want to derive the equations of motion for this system, and the first step is to identify the number of degrees of freedom. In this particular case, mass 1 has the ability to move, and so that gives us at least 1 degree of freedom. If you hold mass 1 fixed, then the cylinder is not able to roll because the center of the cylinder is held fixed, assuming that that's a rigid rod between the mass and the cylinder. So it does not add a degree of freedom, but then mass 2 is free to oscillate even though the cylinder is stationary, so that's 2 degrees of freedom. If you hold mass 1 and mass 2 stationary, then mass 3 can still move, and that would give us 3 degrees of freedom. So this is a 3 degree of freedom system. Okay. What this means then is that there are only required 3 motions. If you notice, I have identified x1, x5, xc, and x3. I should probably also label a variable. I intended for this to be frictionless, like the other one. So I'll define another variable for 2. I'll call that x2. So what I'm going to then do, since there are 4 masses, I'm going to draw 4 free body diagrams. So we'll do from left to right. This would be mass 1. And so what I do is I draw an arrow, or a line, excuse me. Then I label the variable. To get the arrowhead, I pretend that the variable x1 is positive. If it's positive, then the mass is pulling the spring K1. If it's pulling the spring, then the spring is pulling me, and so it's got an arrow this direction. For the damper, same thing, draw a line, put the equation in. Again, pretend that the x1 dot is positive, moving to the right. If it's moving to the right, you're pulling on the damper, and the damper is pulling back. Then on the right-hand side, there's a rod. I have no idea what the force is, so I'm going to solve for it. Since I'm going to solve for it, it doesn't really matter what direction I draw the arrow. I'm going to call it T for tension. Okay, so that's the free minus any normal forces in gravity, which have nothing to do with the motion. That's the free body diagram. So what I'll do then is draw the free body diagram of the cylinder. So the cylinder would look something like this. I have in the center equal and opposite tension coming from that rod. On the bottom, I have a normal force and a friction force, which I don't know, and I'm just going to call it F. I'm going to solve for F. It doesn't matter what direction I draw it. A positive means I drew it correctly, and negative means it goes the other way. Then at the top, I have a spring and a damper. So what I'll do is I'll draw a line in up at the top, and put the equation in for that. The spring would be K2. Now, in this particular case, it's going to be the displacement of the top minus the displacement of mass 2. So I'll put that in. XC is the top displacement, and I subtract x2. To get the arrowhead, I pretend that xc is larger than x2. If it is, then the spring K2 is being compressed, which means I'm pushing it, If I'm pushing it, it's pushing me. So that's a push. Then there's also a damper up there, which I'm running out of space, but I'll just draw it in here. It's going to be C2 XC dot minus X2 dot. If XC is larger than, if the speed of C is larger than 2, then I'm pushing the damper, and the damper then is pushing me. So it goes back to the left. Okay, so let's get mass 2. For mass 2, I have a box. I have a spring and a damper. The spring is equal and opposite to what I have from the cylinder, so I have an arrowhead this direction, and it will be K2 times XC minus X2. And the damper, equal and opposite, and it's going to be C2 XC dot minus X2 dot. Then on the right hand side I have a spring, so I'll have a line. This is going to be K3 times the change in differences, or the change in positions, X2 minus X3. If 2 is bigger than 3, then I am pushing the spring. If I'm pushing the spring, then the spring pushes me, so I have an arrowhead back. So those are my free body diagrams. I have body 3. So I'll draw a free body diagram of body 3. Since everything's measured off of static equilibrium, I don't need to draw the gravity. So the only force really I have is this one here, which is equal and opposite to the one from the previous box. So that's going to be K3 X2 minus X3. And it's equal and opposite, so it is pushing. So if 2 is bigger than 3, for example, then it's being pushed. So I'm pushing it, so it's pushing me, so it's going down. Okay, so these are my free body diagrams. Now what I'll do is I'll write the equations for each of them. So we'll start with the first box, mass 1. If you write the equations, to the right is positive because you can see where the direction x1 is. So I have a minus k1 x1. I have a minus c1 x1 dot, and I have a plus tension, and that equals the mass of the free body diagram, m1, times the acceleration, x1 double dot. The reason it's a positive is because it's a positive displacement in the diagram. Okay, so the next equation is for the summation of forces on the cylinder. So if I sum forces on the cylinder in the horizontal direction, I have minus tension plus the friction minus the spring force minus K2 xc minus x2. Those are all the horizontal. Oh, and I also have a damper minus c2 xc dot minus x2 dot. Those are all the forces, so that equals the mass of the free body. That'd be the mass of the cylinder, we'll call it MC, times the acceleration of the center of mass. I've labeled that as x5, so this would be x5 double dot. Also for the cylinder, I have summation of moments. I'm going to sum moments around the center of mass. So the equation would look like, I guess what I need is another variable for the angle. So what we'll do is we'll say the angle is theta, and we'll choose counterclockwise as positive. All right. So if I sum moments, then I have C2 xc dot minus x2 dot times the moment arm. The moment arm is 1 radius, and that force is producing a moment which is counterclockwise, which is positive. So that's a positive there. Then I have the spring. It's also producing a positive moment, so that's a plus K2 xc minus x2 times its moment arm of r. The only other one is the friction. It's also producing a positive moment, so it'd be F times its moment arm is also radius, and so that equals the mass moment of inertia through the center, call that J, times the acceleration, angular acceleration. So that takes care of the cylinder. Next, what I have is another mass, mass 2, so we'll sum forces on that one. To the right is positive, so I start off with a positive K2 xc minus x2. Then I also have a positive damper, C2 xc dot minus x2 dot. I have on the right hand side another spring. This one's pushing to the left, so that's a negative. It's going to be K3 times x2 minus x3. That's all of the forces, so that equals the mass in the free body diagram, which is mass 2, times the acceleration of the center of mass, which is x2 double dot. Okay, last mass is the mass 3, the one that's hanging down. So that I'm going to sum forces vertically, and so down is positive according to the way I drew x3. So the force is K3. It's positive because it's going down. x2 minus x3. Those are all of the forces, and that equals the mass, which is m3, times the acceleration, which would be x3 double dot. Okay. So now I've drawn 4 free body diagrams. I've written the equations for all 4 of the systems. The number of equations is equal to 5. The variables that are present, we'll just list them out. We have a, we'll get some of the easy ones first. We have the tension, that's unknown. We also don't know the friction force. That's 2. And then the rest of them are all motions. So I have x1, and all of the derivatives for x1. x1 dot, x1 double dot, etc. I have, let's see, x1, I'll go ahead and write them out, dot, and x1 double dot. I have in the next one t I've counted, f I've counted, xc. I have xc dot. I have x2, x2 dot, x5, x5 double dot. Let's see, what else have I got? XC have been counted, XC dot I counted. In the next one I have theta double dot. X2, I think I've counted, X2 counted, XC counted. Okay, there's an X3. There's no X3 dot, but there is an X3 double dot. Okay, so I think I've got them all. I may have to come back and check them again, but that would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Looks like I've got 13 unknowns. Of the 13 unknowns, 11 are unknown flows. But I should only have 3 unknown flows because it's a 3 degree of freedom system. So that means I have more flows than what I should be having. So what I need to do is I need to find the relationships between the flows. Oops. So I'm looking for motion relationships. So what I do first is I look at mass 1 and the cylinder, and what I recognize is that there is a rod that connects the two. So the motion of x5 has to equal the motion of x1. So I'll just write that down. So x1 would have to equal x5. So that gets me one constraint equation. And since I have x5 double dot, what I really want then is to just take a double derivative of this guy. So what I'll do is I'll differentiate this. And so there's an equation for the x5 double dot. The other relationship would be that when it rolls, there's a relationship between x5 and the angle theta. So the angle theta times the moment arm, or the distance between the rolling and the center, is equal to x5. So in other words, theta times the radius is equal to the distance that's moved in the center, x5. Now I just need to determine if it's a plus or a minus. So if I have a positive theta, the x5 moves in the negative direction. So what I want to do then is force a negative sign here so that that sense is noted. So if x5 is positive, for example, then positive 3, then theta would be a negative 3 over r, which is right. It would rotate clockwise instead of counterclockwise. Okay, there's also a relationship between xc and x5 that goes like this. So xc is going to move twice as far as x5 because it's at the it's basically like a lever. So if I were to draw something like this, x5 is in the center. It's essentially rotating around the bottom, and x5 is in the center, and the xc is up at the top. The one at the top has twice the arc, or excuse me, twice the distance from the rotation as the center one. So the top guy is going to move twice as far as the center. So if it were to slide over sideways like this, then this distance there is twice the distance there. So that means that xc on the top will equal 2 times this center, x5. Then I have to think and say, okay, are they positive? If x5 goes to the right, xc goes to the right as well, so yes, it should be both positive. So I believe I've got that one. There is also in the equations xc dot and xc, well, just xc dot. So what I can do is I can also take a derivative of this, and another equation then would be xc dot equals 2x5 dot. And if there's an xc or an x5 double dot or whatever, I can also take another derivative, xc double dot equals 2x5 double dot. Okay, so let's see, I've gotten a relationship between 1 and 5. I got a relationship between 5 and c, and if I'm not mistaken, those are all of the relationships that I have. So if I count the number of relationships that I have, I'd see I've got 1, 2, 3, 4 relations, well, excuse me, 3, and then all of the derivatives. So it looks like I've got about 9 of these. So what I'm going to do is I'm going to show how to fit all of these equations into Mathematica. I'll pause for a moment. Okay, I have opened a Mathematica file, and so on the right side you can see the equations that I'm working with, and we'll go into Mathematica and attempt to reduce these. Okay, so first thing I do is do a quit in Mathematica, just to make sure that if I've been doing something else, it doesn't remember those things. So anyway, what I'm going to do is just type in the equations. So I like to call them EQN, and there's a set of them, so I'm going to use a curly brace. Maybe I should increase the zoom. Okay, so equation, make it 200%. So here we go. I'm going to type in the equations. So the first equation is minus k1 x1 minus c1 x1 dot plus t, 2 equal signs m1 x1 double dot. That's the first equation. Second equation is minus t plus f minus k2 xc minus x2 minus c2 xc dot minus x2 dot. 2 equal signs mass c times x5 double dot. Third equation, c2 times xc dot minus x2 dot times r. I'm going to continue to type these in. I'll pause the recording while I do that. Okay, after a short pause, okay, maybe a long pause, I have entered all of the equations in, and essentially I've tried to organize them a little bit so they're easy to read. The first several equations are from the free body diagrams. One thing I'd like to point out is that I've added in these constraint equations for the motions. For example, here, which we've seen over on the tablet, x1 and x5 are the same, and what I do is not worry whether x1 dot is present in the equations or not. I just go ahead and take the 2 derivatives of all of those variables. It doesn't hurt if you have an extra one, you'll see shortly. So what I do is I establish the constraint and then just take the 2 derivatives. So here's the other constraint that we talked about, and then of course it's 2 derivatives, one there and then the second derivative, and then xc is 2x5 and then the 2 derivatives as well. So total, I have 14 equations. So you can count those. There are 9 of those equations are the kinematic constraints. The semicolon that's here at the end just simply says I don't want to print the results of this. You can print them if you like. In fact, let me do that. I'll just hit enter. And so then here's the output from Mathematica, and it basically copies or tells me what it thinks I did. Okay. So now the next thing is to try to solve these equations. So what we need to do is to think about what it is that is what we're expecting. Since it is a 3 degree of freedom system, 3 DOF, that means I'm going to want 3 equations. So at the end of this, I'm looking for 3 equations that they'll be differential that I want to solve. Now, the order is also helpful. In this particular case, the order is a total of 6. So it's 6th order. So what I'm looking for then is 3 differential equations. Each one has a second derivative. All right, so what I have to do is determine which of the variables I want to solve for, which of the flow variables I want to solve for. I can pick 3 of them. Now, you can't arbitrarily pick 3. They have to be independent. For example, if you say you like XC and X5, that is a bad choice because C and 5 are related. If I told you how far C went, you would be able to compute exactly how far 5 went. Also, theta and 5 are related, so you should not choose theta and 5. Essentially, these are the kinematic constraint equations. Choose variables that are not related through the kinematics. In this particular case, I decide I'd like to maybe solve for theta, x2, and x3. Those 3 variables are independent. So what I'm going to do is type in solve and list the variables that I want to solve for. During the pause, I've done that, so I'll just scroll down in the Mathematica file and show you the what I'm doing. So the first thing I do is I say, okay, the answer is solve. I'm going to tell it I want to solve the equations, and now I list out the things that I want to solve for. Okay, so I'm looking for 3 second order differential equations. So the first thing I do is I say I would like it to find the equations for theta double dot, x2 double dot, and x3 double dot. And those will be my 3 equations, and they'll both have, or all 3 will have double dots in them. Now, since there are 14 equations, I have to list 14 things to solve for. So here I've got 3. Now I'm going to fill in everything else that I really don't care about, but it has to be solved anyway. F and T, obviously, so that gets me a total of 5. And then I'm going to have another 9 values to solve for, which are simply the other motions that come in from the kinematics. So I'm basically solving for x1, x1 dot, x1 double dot, xc, x5, and their derivatives. Okay, so this is typically what you would do. You'd say, all right, I want the 3 or whatever degree of freedom. You have the highest derivatives of those things, and that gets you the equations that you want, and everything else you really don't care about, but you have to solve for them anyway. So I'll hit enter, and out comes the results. So here is a differential equation for theta double dot. Okay, here's the x2 double dot. And if you notice, the only variables that are in these 3 equations right here, the only variables that are in there are the motion variables that I'm trying to solve for. Theta, x2, x3, and their derivatives. The rest of the things are valid if you want them, but I don't care for them, so I'm going to ignore it. Just to kind of clean things up, what I'm going to do is put in some numbers just so things look nice and clean. So here I'm just going to assign arbitrarily some numbers, J, M1, M2, etc. So just grab these out of the sky. The semicolon means don't print the value. and then all I'm asking it to do is use these numbers and print out the answer so it looks a little nicer for me. So when I hit enter, here come the answers, and you can see that here are your 3 differential equations. Sorry for the interruption. Okay, so I've solved these equations and I've put in the values. I just plucked some things out of the sky, and here are 3 second-order differential equations right here. And all of those equations only contain numbers and theta, x2, x3, and the derivatives of those 3 variables. The rest of the things for force, F, T, x1, etc., they're okay. As soon as you solve for the theta, the x2 and x3, you can substitute back in and get the other values if that's what you desire. So this is typically the way these things function. At this point in the class, you don't really know how to solve multiple differential equations. That comes in Chapter 3 and in Chapters 6 and 7. But for now, you've been able to get the equation, so this is what you're expecting. All right, that's it.